and then we can get started. So I am just waiting on this to update. Come on. There it goes. Boom. Awesome. All right, so we are live the right way now.
All right.
Nice. All right, so hello everyone. Thank you all so much for joining us. I have one of my very best friends here. He is going to be helping me with a podcast tonight. We are going to be, I say we, but I'm going to be asking him questions, and he is going to be explaining to me, because I'm a big old dummy about space. This is Two Nicks Talking, and I hope you all enjoy. I will be taking about every 5 to 8 minutes or so. I'll be reading the comments, and if there are any good questions, I'll ask him. He's the one with the relevant education to this. And reminder once more, on TikTok, you will only be able to see me, but hear him. And if you're on YouTube, you will be able to both see us and hear us. So let's go ahead and get started, man. How are you doing?
Doing great. How about you, Nick?
I could be better, but that's okay. It's okay.
Been chilling lately?
Not as much as the James Webb Telescope, I should say.
Yeah, they spent the last 6 months getting down to temperatures because the machines that they use to take these pictures have to operate at such incredibly low temperatures. It takes a little while to get them there. It also took them a little while to get in position to take these pictures.
Why does the telescope have to be that cold?
Because the energy readings that we're getting from these images, or in these images, are in the infrared spectrum, the very, very low energy readings, frequencies of the electromagnetic spectrum. And you have to be, it takes a very special, very sensitive instrument to detect these things, and that usually means it's cold. It means it's isolated from other interference. It means it's very stable, and that takes a lot of engineering and a lot of imagination to be able to create a device that can read the electromagnetic spectrum 13 billion light years away and give us these incredibly beautiful images.
It does amaze me, the difference in resolution between the two, though. Like, what the hell? It's like looking through Swiss cheese versus a piece of glass. It's ridiculous.
The Hubble telescope was much like your classic, barrel telescope you think of, played with as a kid maybe. You saw in movies, but the new James Webb telescope is a much more intricate device. It actually has 12 different mirrors that are like a honeycomb of sorts that are calibrated to reflect light to a single point, and then it goes through a traditional.
I actually read about this.
Apparatus.
It's actually a little more than that. It has all of the big mirrors that reflect to a center point back to another sensor, I think, or even another mirror and then to a sensor or something. And I think I read something about how that is designed to collect as much light as possible, right? To focus it. So is that kind of like how a magnifying glass does with sunlight?
12 magnifying glasses.
Jesus. Aren't these things like 8 feet tall or 12 feet tall or some craziness too?
I don't remember how big they are.
The entire James Webb telescope is 4 stories tall. Did you know that?
No.
Yeah, bro.
Okay.
I read about that. That is a true fact. The telescope itself, I don't know if that's like fully deployed or it's 4 stories tall.
Huge, and they've got to cover that thing in gold foil. We're not going to talk about how expensive that was.
Good Lord. Well, there's a reason it cost $10 billion, and it took like what, 10 years to build?
Something like that.
The name that it's the guy that it's named after, I don't know if he was like flight controller but he had something to do with the moon. Something to do with the moon landing, James Webb. Yeah, so there's a reason that they named the telescope after him. I believe he had something to do with a or the moon landing. I can't remember. So if you guys know, let me know. That'd be awesome to find out. So you talk about that this array needs to be extremely, extremely cold. So I also read that is why it has that ginormagantuan sun shield. Is that correct? And it's like 5 layers thick, and it actually, if you looked at the telescope, if this was the telescope, it actually, and this was your sun shield, the telescope head itself and the sensors and all the mirrors are on this side, and it's got this, like say the Earth is over here, it does like that, right?
Right.
And
to block
it's got
itself from the sun.
Yeah, so
and collect all that solar energy.
yeah, so they were talking about how they had to not only invent ways to solar shield it, but they had to invent ways to stabilize it. Are you aware of the flywheel system, internal gyroscopic flywheel system they use on the JWST to keep it
the mechanicals,
bro? So cool. I get to tell you a little something that you didn't know. I apologize for butting in on the conversation, but dude,
you got your own piece to add.
It's incredible. It's these set of, I think, 3 or 4 wheels that literally the turbulence or the centrifugal force from the wheel turning itself moves the vehicle in space, moves the JWST in space. So it's like they have all these different combinations of these 3 wheels that, just like I said, the energy coming from the momentum moves because there's no, what is it called? No resistance in space because it's the vacuum or whatever. So there's no friction. That's what it is. No friction. So no energy loss, I guess, right?
So because how does it stay in the location that it it took about 6 months to get to a very particular point in space that we wanted to send the telescope to, called the Lagrange point, or a Lagrange point, because when you're at that point, let's jump to that image we've got here. That one makes a little bit more sense when we first look at it. So you've got the Earth, and then you have different L points. And we've sent
the James Webb Telescope to L2, which you see in the orange there on the bottom.
L2 right here. Okay, I see.
And we sent it there because you see the field lines around it that are a little faint, are in the valley. So what you're looking at, like the surface of water, and the denser the lines, the higher the wave.
Yeah, it's elevation, like a topographical map, right? So this is where yours and my discussion about dark matter has come into place, right? That when we do that episode, we need to get some props to visually, spatially show how that works. Oh wow! So special shout out, thank you so much. First 7.5 minutes is perfect timing. There are quite a bit of people watching right now. We've got 6 people watching among Twitch, Facebook, and YouTube. Thank you all so much.
You guys.
And we have 4 people watching in TikTok. Hello, Alien King. Hello, Zach. We are discussing James Webb Telescope stuff. You guys in TikTok can only see and hear both of us, but only see me. On YouTube, you can hear us both, and I will be answering comments about every 8 minutes or so. Trying not to be rude, to let Nick, who's the one who's got the good education, explain to me, the big old dummy, about how this JWST thing works. And because I have a really good question that's just gonna send you off on a tangent.
All right.
Why does looking into space mean we're looking back in time?
Because
I don't want to get off on that tangent yet. That's okay. Yeah. I mean, is it because, literally, the simple answer is, it because in space or anywhere not on Earth, Einstein said that space and time are intertwined, or relative, or whatever.
Light takes time to travel.
Light takes time to travel.
It's that simple.
It's that simple. Okay.
Yep.
I wonder why. I guess that's just a super difficult, non-intuitive concept for human beings to understand. So it takes some time for you to be able to grasp it.
Sounds like I'm in an auditorium.
Oh, it's because I have my microphone unmuted while he's talking to. I'm trying to. That was the one thing that we're trying to avoid. I apologize. Space is super. Hey, Awkward Bestie, welcome back. Hey, Christy, welcome, y'all. Maybe if I kind of sit back a little bit and have this pointed towards me, it'll pick you up less.
There we go.
Maybe that'll be pretty good. Say something again.
How about that? That better?
Oh yeah, my bars are not picking up. So there we go.
All right.
So. Awkward Bestie says space is super interesting, and Christy says came from TikTok, but it sounds like they're in an auditorium, so I hope it's better. Thank you all so much for coming and joining. Hey, Zach. So, okay, so...
Talking about Lagrange
Yeah,
points.
talking about the Lagrange point. Let's get back to the subject. Go ahead, go for it, sir.
That's all right. So, it's at the Lagrange point because it's far away from Earth, it's far away from the sun, it's far away from any electromagnetic interference, and it's going to stay at that point in orbit with the Earth for basically free. It doesn't take any rocket power to stay at that point. And so it's stable, and it's a very nice observation point.
So I have a quick question. Is this the 1.5 million kilometer point away from the Earth that they're talking about that they sent the James Webb Telescope?
Yep.
Whoa! How did we manage to send something that far away? How do scientists? Is that just calculus?
That is a lot of calculus.
That is a lot of. Is it called? Does it have a name like celestial calculus or something? Or is that what calculus is of the celestial bodies?
It could be said that, but it's multivariate calculus, rocket trajectories.
Multivariate calculus. That makes so much sense to me now. Christy says so much better. Perfect.
Thank
awesome.
you.
So we don't sound like in an auditorium anymore. Awesome. So, okay. So the story goes with Newton, if I'm not mistaken. He realized he didn't have the math. If he asked the question for the ages, he said, if the apple falls, does the moon fall? And then he went in Cambridge because, it was during the Black Plague, and he figured out that they didn't have math to calculate celestial bodies, so he invented calculus. And I think he was 21, right? 23, 21.
Mm-hmm.
But, so if it really is multivariate calculus, and calculus, my ass needs to start learning some calculus so I can start understanding these concepts, at least conceptual calculus, like what things are. I'm not trying to be a mathematician or anything, but it would be great to learn the terminology.
Yeah.
So, Lagrange point, we're talking about here, everyone, where the Earth, NASA sent the James Webb Telescope to be able to, is it geosynchronous lock with us, whatever the fuck it's called, that the moon is, to where the sun shield's always towards the sun or whatever, how they did that? What's that called? Do you have any idea?
I don't remember exactly. I think it's a heliocentric orbit that's in lockstep with the Earth.
Okay. We don't have to get too technical about that. I was just curious. Okay, so you were telling us that this is a very schmoozy, comfortable point for us to be able to send observation out into space, and before you were rudely interrupted by me. Sorry about that. And what were you about to say next?
So we're looking out in space, and let's go back to that first deep field image. We're looking out in space, and if you look real close at this, you'll see that there are orange and red smears across the center of the image. Like make little circles with the mouse.
Yeah, right towards the center around these smears here.
So
now, while you're talking, keep going. I'm gonna do something for the stream. Keep talking.
So what you were looking at here are stars and galaxies that are significantly farther back in space that have been remagnified by the gravitation of the area that we have pointed our telescope at. So we're looking at a galactic magnifying glass. So we have two layers of stars, layers, quote, as layered as stars can be. We'll show more pictures about that here in just a minute. But so we've got two very different fields of stars we're looking at, and so this is called the deep field image. And the reason that we can see these reddish smears is they are galaxies that are further away from the image that we focused on, and they have shifted to the red spectrum as energy fades as it travels over time. And so yes, exactly.
Oh yeah, red shift, blue shift. I'm glad that you're actually bringing this up. You and I had this discussion yesterday, and this is actually one of the things that I was very, very curious about. Please continue.
So, you notice the stars that are colored, that have blues and purples and greens and yellows. Those stars are the closer field to us, and the further back you go, the more red faded orange, deeper colors they are, because the energy over time in the photons of light has dissipated all the way down below the visible spectrum into the the infrared spectrum.
Yeah.
And so that energy is being picked up by these extremely cold devices, these very sensitive devices on James Webb Telescope, and it's being digitally enhanced so that we can now see it in this image, because we literally cannot see this. It's like looking through a night vision goggle.
So this is that natural telescope you were telling me about. Why does this kind of remind me of, not a fisheye lens, but why does it look like it is?
Comparison.
So what exactly is it that's distorting
Perfect question.
The light, is it something that we can't see that's bending around it? Is it this like smoggy galaxy that we're looking through that we can't see or something?
Let's take another look at the pictures of Laniakea that we have. Next, so here we can see the galaxy superclusters and the way that they group up. And it just so happens that these, groups of galaxies have energy, and when we look through this very particular point, the energy of those groups of galaxies had condensed in such a way as to create that lens that we're looking through.
And that comes from how you and I discussed what dark matter does to the fabric of space and time, how it creates these peaks, and then the valleys is where the gravity pushes everything into like water, right?
Yep.
Water
and
flows.
We've got another picture of Laniakea that shows the way things flow a bit more.
This one, is it this one?
Yes, that's
okay.
it. That red dot that we see there is our galaxy. And
whoa, that still blows my mind. This picture, I love it. I love it.
So basically, somewhere in the very, very dense, bright region of this image, it could be a gravitational lens that we could look at, because the brighter this image is, the more energy intense
something like
is.
This.
Exactly.
Whoa.
Yep.
Oh, I understand now. A super condensed form of energy that acts at... Oh my god!
Ding.
That's amazing.
Mind blown.
It is. So is there a way to detect these super thick parts of space?
Detect? I think it's more of a happy accident we find them.
What if we were to shoot light through it and then to measure its speed somehow?
We've mapped most of the sky at this point, so we know where most of these are that we can see. And that's also a very key point. Just because it's there doesn't mean our perspective will allow us to see through it.
Great point. Great point. And I feel the need to point out, just because we see it here in these images doesn't mean that it's actually still there in real time either. Something that's traveled 13.8 billion light years across the universe. How old's the Milky Way galaxy?
I think the Milky Way is 14.
Oh wow, so I don't know why these facts always went over my head. It's literally the same. Like, it's interesting to know that our galaxy was formed right close to the central point of the Big Bang. Ha! Christy says, my brain is hurting. No! Take some Excedrin. No headaches. This is good talks. Hey, my brain hurts at first to it. It cracks and then it makes room for new information. That's what happens. That's what happens.
Welcome to the deep end. Welcome to the deep field.
The deep field. I love it. I love it. I love it. Okay, so we're talking about super thickly condensed energetic parts of space that would allow the magnification. Oh wow, look at this one down here at the bottom. Wow, that's amazing. Just at the little swirly one. Every time I look at this picture, I always see something new. It's incredible. But and I just felt the need to point out about how light that comes from the oldest parts of the universe, we just don't even know how many of these have already blipped out of existence.
That's absolutely right.
It's unbelievable.
That is, and so looking at these images, scientists hope to be able to analyze the very early composition of the universe and be able to, these are literally the most clear images we've ever received of the deepest part of space that we can still observe. The closest that we could possibly get to Big Bang-like conditions exists in these images and the signals we're getting from James Webb Telescope today.
I've always been curious why they chose this specific, literally, they said if you hold a grain of sand out at arm's length, that's the area that this covers. And I wonder why they chose that area. Is there a reason, you think?
I don't think it's more of a choice. I think it's more of that's just a good comparison. That's how it happened to be created. So it's a reference of that.
Okay, that makes sense. I was just curious if there was like a direction of creation, because I was also watching a video about physics last night, the Great Expansion, and it said when we look out into space and we try to see where there would be an origin of expansion, we can't seemingly find an origin point of expansion. It's seemingly expanding from everywhere simultaneously, faster and faster and faster. But that's what makes it so confusing. But I have a theory. I don't even want to call it a theory because theory has math and everything. I have a hypothesis about this, and I'm curious if it's an expansion from point space-time. Literally, well, point is nothing. I'm just of every point, and then
there's a theory out there called hyper black. The theory's title something a 4-dimensional black hole has been mathematically shown to show similar characteristics to a black hole.
Wow.
Or not a black hole, a Big Bang. Sorry. So the theory is that a 4D black hole could be the Big Bang, like event that created our universe, and that would
just sucking up all kinds of higher matter and spitting it out in a way. You know, I've always said that third-dimensional matter is sound interference cross sections. That's what matter is. It is the cross sections between vibration and frequency, sound and light, and it creates solid matter because it creates these intersections. Because I remember watching this wonderful
I have a question. Christy, no, that is not an artist rendition.
That's the actual image, right?
This is the actual image.
Yeah,
the
we no
only
longer have to use CGI, and that's the one thing that made me so excited about this. Is it's no more data, and then they send it off to be rendered. This is what we have.
Right. This image was taken in approximately 12 hours, and the only additional rendering that's been done to it is to adjust the color spectrum from the infrared cameras so that we can see it in these deep red images.
And I actually found out why they color these. It's not just red shift, blue shift. It's the element composition.
Yes, that is an additional thing that we can tell from these, and that's what we hope to learn more about, how we hope to learn about the early conditions of the universe by studying the elemental composition
that
of
blew
these
my
images.
mind so much that we could literally look at a faraway star or planet or anything, exo whatever, and we can read its I don't know if telemetric,
spectral lines.
Spectral lines, and we can understand what element it is. And I would love to do a react to this kind of stuff because science, you know, has always been something that I've always loved, and I would love to. Oh, the cosmic cliffs, yeah. He was talking about why we actually have multiple types of sensors on the JWST itself, and why infrared is the most important. And you and I were talking about seeing through the cosmic space dust.
Yes.
And can you explain a little bit about, like, do you know the science, like why it's possible and stuff?
Sure,
cool.
Sure. So what happens? We take the light that is, the wavelengths of light that we receive. We analyze them in such a way as to find the spectral lines that produce them, and those spectral lines
is that spectroscopy?
Yes.
Ah, cool. I remembered a word.
Chromo
Yay.
something.
Sorry.
Maybe, yep, chromospectroscopy, something like that. I don't remember the technique name. Yeah. Yep, because we're looking for spectral lines, and those are unique to elements. So we can pair up and combine the right spectral lines to say it has helium and nitrogen, phosphorus, iron, all these elements.
Yeah. I'm asking this for a very important reason. I made a video on my TikTok that you're gonna laugh at me. I have a confession. I have been researching flat Earth. I've been researching flat Earth. Not as a believer, but as a person who wants information. Whether I need to come to Jesus moment. I let my hair down too, but it's a little dirty at the moment, but that's all right. But no, I obviously never believed it, but I wanted to know what they know to build a good argument against it, which it's already easy to disprove it. All you got to do is they did some argument on, or some experiment on a Netflix show, and they were like, oh, well, I guess we kind of fucked that one up. But, shoot, I kind of lost my train of thought. Sorry. Infrared. Shoot, back me up a little bit. Damn.
So let's go a little bit further back to this Laniakea image, and then talk about where this comes from.
Oh yeah, your space bubbles. Go for it.
All right. So this
Oh, I remember the flat Earth. Okay, spectroscopy. Okay, that's what I was gonna say. Just real quick, I remember now. I apologize.
Spectroscopy.
Yeah, that is the definitive defeating argument against flat earthers. Is because we could literally, scientifically, that is the one proof that I needed. If we could literally measure the wavelengths and go, we know what this is, because we have science and math that tells us what this shit is, and it's repeatable over and over and over again, and that to me is proof that we ain't flat. Okay, please continue.
We ain't flat. So another really neat thing that spectroscopy has shown us is we've been able to look at the Milky Way galaxy in this picture and see X-ray and gamma ray energy emissions coming out of the Milky Way, like this which are what those giant purple bubbles are. So the Milky Way is just in a disk. You know, we're looking along like the side of a frisbee, basically.
Ooh, you just gave me a great question. Don't let me forget, why can't we see ultraviolet? Going ahead.
So, you know, we're looking along the side of the Milky Way like a frisbee, you know, the edge of it. But then the energy that's coming off of the Milky Way itself is, you know, got these incredible shapes in the X-ray and gamma ray spectrum, and we're still studying what this exactly means, but this, you know, gives us a closer picture of what the energy that a galaxy can produce and how this type of energy collects into something like this, and then collects into Lana Kea itself. And I'm waiting on stream to catch up. Switching a little bit too fast.
Oh no, this is us in real time here.
Okay.
So as you're talking and switching here, it's in real time. You're good, buddy. Go ahead.
So you know, as it's building up into Lana Kea, and then we can actually look at the beautiful results that are billions of light years away.
That is so astounding to me, and it blows my mind. It just, everything goes back to the resolution. You know, this is such a, I wonder how, man, it blows my mind to think that there is math that dictated the size of the mirrors and how all that works, that allowed us to be able to absorb that much light, you know. And that kind of takes me back to the question about seeing in ultraviolet or whatever, and I believe I already know the answer, and I think it has everything to do with detecting microns of wavelengths, right? How long they are, or at least the difference, or the length of time between each of the peaks, right? Isn't that a micron measurement or something? I'm saying this very wrong, but I don't know. Because I know that JWST measures between like 0.2 microns to like 25 microns, which is why we can see infrared. But I think ultraviolet's like way faster.
It's on the other end of the spectrum.
And then so you got ultraviolet, and then, so what would be on the other end of that then?
Well, it's either infrared or ultraviolet, and in between there is visible spectrum.
So is there anything past infrared, I meant? Not to sound like a dummy.
I forget. You know, let's pull up the electromagnetic spectrum. There's a really cool image of the EMAG spectrum that's
worth looking at here.
Images. And I know exactly what I'm looking for.
There, that one.
Right here?
Good. Yeah, that works.
Radio. There we go.
Okay.
X-ray, gamma ray.
Yeah.
So they just call it radio, and then the higher the frequency of radio, it turns into infrared?
Yep.
Oh, wow. Damn, I didn't know gamma ray was the highest. I didn't realize that. That's cool. No, you're fine. I was just hearing my dog scratch over there. Adley, you need to go out soon? All right, I'm sure you do. Okay, so this is cool. I didn't have any sort of frame of reference for the light spectrum, so this helps out a lot. Oh, wow, so atomic structure is on the X-ray size? Whoa. I wonder why bone X-rays are X-rays then. I wonder why they had to do that. Is it to see through, like, you know how an X-ray, when you get like a broken bone or something?
That is the frequency
that they use.
I wonder why though. I wonder if it's to see through this stuff, to just ignore this molecular stuff above it to get through that, to see, you know what I'm saying?
I see your point, yeah.
I don't know.
Yeah, that makes perfect sense.
My brain asks weird questions.
It's gonna show the atomic structure rather than the molecular one.
Yeah.
That makes sense.
That's really cool. That's really cool. Okay, please continue. Where were we? Linear
You were asking about
why we can't see the electromagnetic.
Yeah.
That very high radiation level, because that would be it's the ultraviolet spectrum comes from the sun. We feel it as heat. It would damage our eyes to damages your eyes to sun like that. So it would be experienced as heat, or more blinding pain, like from a welder's arc. It's certainly in this.
Oh yeah. Okay, I understand.
That's why we can't look at it or see it.
Okay.
A black light is about as close to ultraviolet as you can get.
So,
what is the frequency of black light? That's a good question.
That is a good question. What is a black light's frequency? 365 nanometers? Huh. I guess they're ultraviolet?
That makes it.
Hit the spectrum there.
Right here? Oh, this right here? Okay. Short wave, middle wave, long wave, visible light, infrared. Oh, that's not very helpful.
No, it puts
360 on there. So we
oh, okay.
So it is.
It's a long wave ultraviolet.
Yep, but
That's
it's
cool.
also low enough energy not to be harmful.
Nice.
And that's another point.
What's the sun like way down here?
I don't know off the top of my head.
What is the sun? If the sun is a deadly laser. The sun's light frequency. 10 to the 18 hertz. Oh, I guess it's not the quality, it's the quantity from the sun that's hurting you. Maybe. Or like, what am I trying to find here? Like, what is the sun's ultraviolet wavelength? There you go. 2 nanometers.
To 10 meters.
You know, that actually makes sense because they say that there is. I've heard
broad spectrum.
Yeah, broad spectrum. I've heard that. Physical science for the win. I told you guys, I haven't done science or anything like this since like the fucking 6th grade. So I was a big old dummy to this kind of stuff, but that's okay. That's okay.
I think that's all I've got. Do you have any questions about the James Webb Telescope?
Yeah, we'll leave
anything
this
we talked
open
about?
to questions now. That sounds like a good idea. And it's right at 32 minutes, so that's perfect. Perfect. Nice presentation, sir. I do really like this, though, how the distortion of it, like you said, is the natural telescope eye in the sky to be able to see further than we ever thought possible. I'm just curious about how much of this is from that and how much of this we would have been able to see just because of the JWST timeline, you know? Hey, Mama, no problem. Welcome back. So, it's all good. Doesn't look like we're gonna have many questions, but that's fine. This is our first episode. I want to thank you for coming on, my dude.
Thanks, bro.
And everybody, this is probably gonna be maybe once a week, maybe once every 2 weeks type of thing, but we're gonna definitely be making more episodes.
When it's on YouTube.
Yes. Hit that subscriber button on YouTube. Oh, it's you, Christy. Oh, that's cool. Oh, you were just on YouTube. Okay, cool. You went back to TikTok. That's awesome. So yes, everybody, hit that subscriber button on YouTube. Subscribe for more. If you have any topics that you want us to talk about for the future, let us know. That would be really cool. We're definitely going to plan some stuff out, and we're going to have a lot of fun with this, man.
Yes, we will.
Thank
Lots
you.
of science news.
Thank you for the
Interesting
education.
shit. Yes, sir. And there's still lots of questions to be answered out there.
Oh, without a doubt.
Lots of questions.
Without a doubt. And I'm excited for what NASA can show us tomorrow. Seriously. And the next day, and the next day, and the next day. So thank God for NASA. Thank the universe for NASA. So thank people for NASA too, because they're the ones who did it. So, and thank you guys for watching the show.
Thank y'all.
And we love you guys. And we'll see you guys next time. Y'all be safe. Peace.